Recorded.
All right, so we're going to go ahead and get started. Some of the people online are going to be missing for the first few minutes, but hopefully get their audio connected up quickly. Welcome to the third day where all the great papers are. We're doing embedded security and hardware synthesis today. Our first speaker is Christina Delimitrou. She's an assistant professor at Cornell. I bet you she thought she was done giving conference presentations, but unfortunately, I think your student came down ill, and so she's filling in. So I'll let you take the first talk. And if you're the second presenter or you know the second presenter, could you reach out to me? Come find me over on the side. Thank you.
All right, great. Good morning, everyone. Thank you, Ron, for the introduction. So yes, obviously this work was done by several students. Unfortunately, half of them are stuck abroad and the other half are done with COVID. So we'll have to make do with me trying to present this. Anyhow, let me first give you the one-slide summary of this work. So in addition to cloud systems, edge swarms have also increased over the past few years, both in size and in complexity. And that has both enabled new types of IoT applications, but it also means that we have to rethink what the cloud edge system stack needs to look like. There are several challenges that we'll talk about in a bit more detail across the system stack. So from the software side, at the programming interface level, we want to abstract as much of the complexity of writing applications for these hybrid systems from the end user as possible. We want to automate as much as possible the data and task placement in these frameworks. We want to either build or identify an existing execution environment that matches the fine-grained, highly data parallel, intermittent, and short-lived nature of IoT tasks. And finally, at the hardware design level, we need to first identify the resource bottlenecks and then design the hardware in a way that reduces these overheads, especially when it comes to network communication and data transfer. And also design the hardware in a way that is reconfigurable so that it can adjust to the frequent updates of both cloud and edge applications. So I'll tell you a little bit more about HiveMind, which is an end-to-end hardware software system stack that we have built for cloud edge systems, which tries to address these challenges. On the software side, HiveMind implements a declarative programming interface that abstracts the complexity of writing applications for these hybrid systems. It automates the task and data placement operations across different devices. It leverages serverless or function as a service compute, which matches the characteristics of fine-grained IoT tasks. And finally, it implements two types of reconfigurable hardware acceleration, one for network processing and the other for data transfer. And I'll show you that this offers significant performance, efficiency, and programmability benefits compared to previous either cloud-based or edge-based solutions. Now, before we see more about the design of HiveMind, let's go a little bit back on the motivation. What are the characteristics of the applications and systems that we care about, and what are their constraints? So in the 15, 17 years that cloud computing has been around, it has gone from supporting a small number of large applications to hosting practically every application from every domain of human activity. These are applications that we have come to expect high performance, low latency access at any point in time and from any place in the world. And many of these applications run purely on cloud resources in large scale data centers where resources are plentiful. Over the past few years, an increasing number of applications has also a component of their computation and data, which resides on edge devices. And there is a wide spectrum of these edge devices. They range from relatively powerful ones like smartphones or tablets, which have quite a bit of compute, memory, and network capabilities, to very low power devices like drones, nanosatellites, sensor networks, and small, simple terrestrial robots. For the purpose of this talk, I'll mostly focus on the latter, the low power devices that are resource constrained. And even more specifically than that, a lot of the results that I'll show you are based on drones. The design of HiveMind is not specific to drones, but they are a good use case for these low power edge devices. So what are the applications that we care about? These range from relatively simple single-tier applications where we collect data from the sensors, do a computation, produce an output like face recognition, item recognition, simple analytics, and so on, to more complex multi-tier applications with multiple phases of computation and data transfer, where we can implement scenarios like disaster recovery, digital agriculture, complex ML analytics, routing, and navigation. These are applications that are interactive and latency critical, so we care about their tail latency more than their average latency. They have to meet user-provided quality of service or SLA constraints. We also want to minimize the battery consumption on the edge devices. And finally, especially because these are low-power devices, they're not very reliable, so we need to be able to address failures in them. So now, given these constraints and characteristics, we designed HiveMind, which is a hardware software system stack for cloud edge systems. It primarily focuses on low-power edge devices, and it primarily focuses on the more complex multi-stage computation scenarios where we have multiple phases of compute and data transfer, and these are becoming more prevalent in edge swarms. Let me tell you a little bit about the methodology that we'll use for the rest of the talk, and then we'll go into more details on how HiveMind is designed. So again, for the purpose of the talk, I'll focus on programmable drones. The paper has more details on how to port the framework to other types of swarms like terrestrial robots. So for these results, we're using a set of programmable off-the-shelf drones. These are Parrot AR2 drones. They come with a small ARM core, a little bit of memory, and an extra SSD for persistent storage. And then in addition to those, we have 20 servers in a backend cloud, and these are server class 2-socket Intel servers with 80 logical cores and a few hundred gigs of memory each. The applications that we care about are both single-tier tasks like face recognition, weather analytics, obstacle avoidance, and so on, and the more interesting, more complex applications with multiple phases of computation and communication. The two that I'll talk about today, the one we call the treasure hunt, and that's the one that you see in the figure on the right. So drones are distributed in a baseball field, and they have to identify the number and location of a set of tennis balls. The second scenario is a little bit more complex. Instead of tennis balls, we have people. People can move, so then we also have to disambiguate between the people that different drones have detected. Okay. So let me give you an overview of the different layers in the HiveMind system stack, and the paper has more details about each one. So from the top to the bottom, if we look at the programming interface first, HiveMind implements a declarative programming interface, the HiveMind DSL, where the user can express at a high level the task graph that they're trying to deploy, information about the individual tasks like the logic, input and output data, and any constraints or properties that different tasks might have. The DSL, the compiler, and the code synthesis tool will then synthesize the end-to-end code base, including the APIs between different tasks. The reason why I'm focusing on the APIs is because for multi-tier applications, even those that run purely on cloud systems, APIs are the main source of bugs. So we want to remove that burden from the user and try and synthesize them automatically. Let me give you an example of what this looks like. So in the bottom, I have an example for the second scenario, the one where we want to find the unique number of people in a baseball field. And the first thing that the user will specify is a task graph. So what is the list of tasks they're trying to execute and the end-to-end constraint of this application. In this case, the end-to-end constraint is in terms of performance. So this is the latency of the entire job. This could also be power, it could be cost, or it could be combinations of those three metrics. Then they have to specify some information about the individual tasks. So what is the input and output of each task? What is the logic that they have to perform and any properties? So this is an example for a task that collects images from each of the edge devices. It has several dependencies. It has a parent task, which is the one that creates the route that each drone has to execute. And it has two children tasks, one that does the obstacle avoidance so that the drone doesn't hit any buildings or trees or other drones, and the other that does the face recognition, which tries to find people in the field. And the same process continues for each of the tasks. So the face recognition task will specify input and output data, the model that they want to use, training data, and specific properties, and its dependencies. So the final dependence is the face deduplication task, and this is the one that after we're done identifying all people in the baseball field, we want to disambiguate them so that we arrive at the unique number of people. Now, in addition to that, a user can optionally provide properties or constraints for the different tasks. These properties can extend from synchronization. For example, which tasks can run in parallel versus which tasks need to be serialized. They can extend to learning abilities. So if we have a machine learning based task, we can allow the framework to retrain that task if the accuracy drops below some level, either on the individual edge device or swarm-wide. And they also extend to scheduling and placement constraints. For example, if the user knows that a task always has to run at the edge, they can specify that. Or if there are two tasks that are mutually untrusting, they can specify that they should never share a cloud server or an edge device. From that information, the compiler and code synthesis tool generate the end-to-end application code, the inter-task APIs. And specifically for the APIs, they generate different versions of them, depending on whether each task runs in the cloud or runs at the edge. Now, having this information, the next step is figuring out how to place the tasks and how to place the data. What I'm showing in this figure is the two extremes. So the case where we either run everything in the cloud or we run everything in the distributed edge. On the left side is for the simple single tier applications. On the right side is for the two more complex end-to-end scenarios. The left set of plots show the distribution of task latency when we run everything in the cloud, and the right when we run everything at the edge. So what can you take away from this? The first thing to take away is that, which is not very surprising, that the edge has much fewer resources compared to the backend cloud. So usually performance is better in the cloud. In addition to that, performance is more predictable in the cloud for the same reason, and also the fact that the network connectivity from these low power devices is not very reliable. That being said, that's not the case for every task, or it's not the case equally for every task. There are some applications like obstacle avoidance and like the weather analytics, where running at the edge doesn't make a big difference. And the reason for that can be that that task is very performance critical, so you cannot afford to offload the data to the cloud, or the computation is very lightweight and you can run it just as well on the limited resources of the edge devices. The main thing to take away from this is that there isn't a one-size-fits-all solution. We have to look at the individual tasks and see what should be placed at the cloud and what should be placed at the edge. So overall, this is something that we don't want to burden the user with, and we want to try and do it automatically as much as possible. HiveMind takes advantage of the fact that we just generated different versions of each task and each task API, depending on whether it runs in the cloud and edge, to do some lightweight profiling of a small sample of each task, identify what is the latency and power measurement, and then from that estimate what performance, power consumption, and cost you would get for different placement strategies. And from that, it selects the one that most closely matches the constraint that the user specified. Now, for computation that runs in the backend cloud, we still have to either design or identify an existing execution environment or deployment strategy that matches the fine-grained, intermittent, short-lived, and highly data parallel nature of IoT tasks. Function as a service or serverless does that, and it offers both opportunities and challenges when it comes to offloading IoT tasks to it. This slide shows the opportunities. So the figure on the left shows the performance comparison of a serverless deployment to a reserved fixed platform as a service deployment across different applications. And the main thing to observe is that usually serverless gets much better performance, which is not surprising because it can adjust very easily to fluctuations in user load by spinning up more resources. The second advantage is that serverless addresses very gracefully failures, either failures in the edge devices or imperfect data that was collected by the edge devices, which is very common. At the same time, there are several challenges that serverless presents. The first one is that performance is much less predictable on serverless compared to a fixed reserved set of resources. And there's three reasons for that. The first is instantiation overhead. So if the resources are not available when a task needs to run, new containers or VMs need to be spun up, and then the task can start executing. Second, tasks in a serverless environment do not communicate directly with each other. They have to go either through a controller or a database or a remote storage system, and that adds a lot of overheads. Third, because each task in serverless is much smaller, you have much higher degree of multi-tenancy in a serverless environment compared to a traditional platform as a service environment. That contributes to contention and performance unpredictability as well. So the figure on the right goes a little bit deeper into where these overheads come from. So we break down the end-to-end latency for each task to execution, data movement, and instantiation and other control overheads. And you see that in many cases, less than 50% is useful work and more than 50% is everything else. So that's something that needs to be addressed before serverless can be viably used for IoT tasks. The way we address this in HiveMind is by building a centralized cloud controller. This is implemented over OpenWhisk. And OpenWhisk is a widely used open source serverless framework. We're using a centralized controller to have global visibility, both on the cloud and edge resources. HiveMind also uses caching of container images and pre-warming containers that with a high probability will be used in the near future. The reason why we can do this for IoT applications is because they have very periodic patterns. For example, every how often they collect sensor data. This controller also tries to optimize data movement between dependent functions by placing them physically close, if not in the same container, then in the same server whenever possible, or using pub/sub message passing models to optimize data transfer. Even with those optimizations, there's still a significant amount of time that is spent transferring data between dependent functions. So this still motivates the need for rethinking what the hardware design should look like. So if we go at the hardware level, the figure on the left shows how much time of the overall latency of each task is spent for network communication and data transfer. And you see that especially for tasks that don't have a lot of compute, this can be more than 50, more than 60%. And it gets worse for ML heavy tasks, which transfer a lot of data. And it gets worse when the network connectivity of edge devices becomes unreliable, which is often the case for these low power devices. So to address this, we built two reconfigurable acceleration fabrics in HiveMind, one that optimizes the cloud edge communication, so data offloaded from the edge devices to the cloud, and that's over RPC. And the other one is optimizing data transfer between serverless functions in the cloud, and that is done over a simplified RDMA protocol. Both the two acceleration fabrics are built on the same FPGA, and this is a tightly coupled FPGA which interconnects with the CPU over a cache-coherent NUMA interconnect. The reason why we want a specific interconnect is because both these operations are very data intensive, and having a cache-coherent FPGA means that we don't have to copy data between the CPU and the FPGA. So we're spatially partitioning the accelerator, and that allows us to support multi-tenancy, both for different types of acceleration and also multiple instances of the same type of accelerator if we have mutually untrusting applications on the CPU side that we don't want to share a NIC or an RDMA engine for. Okay. In terms of implementation, it's a relatively large system. So on the software side, it uses mostly C++, Python, and Node.js. The hardware accelerators are built on Verilog, System Verilog, and Vivado HLS. It's a centralized controller with hot standby copies for the case of dealing with failures in the controller, and it has an end-to-end monitoring system that goes from the cloud to edge and back. There are some other features that I'm not going to have time to talk about for fault tolerance, online learning, and straggler detection. And let me just show you a quick overview of a comparison of this system versus purely cloud-based or purely edge-based systems with and without the use of servers. Okay, so this is a small snapshot of the performance comparison across all applications. Again, the simple single-tier applications are on the left, the more complex scenarios are on the right. We've already seen the distributions for the cloud and edge plots. So the new thing in this figure that you should focus on is the HiveMind plots. And two things to note here are that first, performance is better. That's not surprising because we're careful about how to partition the work across cloud and edge, but also performance is more predictable. And that is where hardware acceleration helps a lot because it reduces the amount of queuing and the amount of jitter in performance in network communication and data movement. And that also translates to the results for power consumption and network bandwidth usage. So the last thing I wanted to show is modularity. So there's a lot of different components in the system. So it's important to know first how much of the benefit does each component contribute? And also, can we use subsets of these techniques and still get some benefit if, for example, there aren't FPGAs available in a cluster? So this is what this figure shows. The leftmost bars show the full HiveMind system. The next set of bars shows centralized and distributed execution with different types of acceleration. And finally, the last bars show HiveMind, but just the software side without acceleration. So what can you take away from this? First, the system is modular, so there's still benefit to be had by using subsets of techniques. If, for example, acceleration is not available or a serverless deployment is not available in a cluster. But to get the most performance and efficiency benefit, we have to tackle both the software and hardware bottlenecks of these platforms. There's several other experiments in the paper that I don't have time to go over for latency breakdown, fault tolerance, scalability, and portability to other swarms. Let me briefly wrap up by saying that edge swarms are increasing in both size and complexity. That has enabled many new interesting IoT applications, but it's also required rethinking what the cloud edge system stack should look like. There are several challenges, both on the software and hardware side. HiveMind is an end-to-end solution to address these challenges through a declarative programming interface in the software, automating task and data placement, using serverless for quick cloud offload, and using reconfigurable hardware for network communication and data transfer. And that offers significant performance, efficiency, and programmability benefits. And let me also show you the students who did all the hard work for this project. Thank you, and I'm happy to take any questions.
We have some time for a couple of questions. Yeah.
Do you think there? Okay. Do you think there would be any benefit in running part of the application on the edge and part of the application on the cloud?
That is a good
Or-
question. Yeah. Oh, sorry, go ahead.
Okay. Or do you think that would inherit the worst of both worlds?
That's a good question. So in some sense, that is what HiveMind does, but it does it at task granularity. So a task can be face recognition. Another task can be creating the route for navigation. So one of those can run at the edge, one of them can run in the cloud. What we haven't looked at yet is intra-task division of work. To some extent, well, okay. Let me think about it. That introduces a challenge, which is that you have possibly increased data transfer between cloud and edge. So there is a trade-off of how fine-grained you want to go. That being said, there is an orthogonal problem, which is once you offload something to the cloud, or even in the hardware at the edge, you can have a hardware design that supports very fine-grained tasks and potentially speculative execution of fine-grained tasks, and that you can still use with this platform. But I don't think we want to burden the user with specifying intra-task.
All right. We got time for one more question here.
Thanks. Hi, Sabrina Newman from Harvard University. Very cool work, very comprehensive. And I guess maybe a little related to the previous question, I was wondering, what's the relationship between this work and the robot operating system, ROS, and sort of the cloud robotics work that's been done there?
Mhm.
Is it about like the granularity? Is this complementary? Could this be interfaced?
It's complementary. That's a good question. So what we try to do here is not change too much about existing frameworks. So the operating system is still the operating system that you have in normal cloud and edge environments. What we have changed is the programming interface. And the idea is to take it to a higher level. So try and let the user focus on the high level objective. What is the performance, power, or cost that they want to meet? And then let the system automate where tasks are placed, how APIs are being synthesized. So it's a slightly different goal, but I think to some extent they're complementary.
Very cool. It'd be neat to see these things put together, I think.
All right, let's thank the speaker one more time and question askers. Get our second speaker, Marcelo. Ready to connect? So while Marcelo is getting connected, if you're just joining us, we had a bit of technical difficulty with audio when we started. So if you were expecting to see a different talk when you were walked in, you might be seeing it now. So we're running about 10 minutes behind the listed schedule. Our next speaker is, let me grab a bio here real quick. Is Marcelo Orenes-Vera. He is a third-year PhD candidate at Princeton. He focuses on accelerating applications by tackling memory bottlenecks. He does that with hardware, software, co-designs spanning from modular hardware RTL design to software programming models of new architectures. The fun of hybrid, we have to make sure we get our screen shared correctly. Very good. And is the audio connected now over to the, okay, good. Sorry, everyone, particularly if you're online, that's a lot of noise. Good on your- Did you get this all set up? Perfect.
Yep. So yeah, hello everyone, and welcome to this talk on design. How's the slides is. This is so zooming. Well, I think it will be fine. Yep. Welcome to this talk on designing and realizing scalable latency tolerance on Manycore SoC. My name is Marcelo Orenes-Vera, and I've done this work in collaboration with my colleagues from Princeton University, UC Santa Barbara, and the University of Murcia. System designers are employing accelerator-oriented heterogeneity and parallelism in order to speed up the computation. While these trends have greatly benefited compute-bound workloads, there remains a class of applications, those that are memory-bound, which remain difficult to accelerate. And many of the graph applications, recommendation systems, and sparse neural networks fall into this category. These applications are very important for data analytics, as the data footprint is constantly increasing, putting more pressure on the memory system. These workloads contain indirect memory accesses that arise from pointing direction, like A of B of I. Since array A is in order of billions of data points, IMAs incurring poor cache locality, and their latency dominates the runtime, as we can see in the figure of the right. Many core architectures often have slim cores without out-of-order structures and cannot achieve memory parallelism. A prefetcher in each core causes per-core overhead of prefetching structures and buffers. Moreover, heterogeneous many cores might want to provide the specialized data supply to accelerators too, and solutions in the last level cache or the hierarchy are not easy tasks. So we wanted something that could be easily integrated into an SoC framework. And although some of the prior work proposals in microarchitectural changes might seem lightweight at first, just the fact that the IP block is being modified creates a heavy verification burden. Recent trends in open source hardware promote SoCs made of composable in-house and third-party IP blocks. And you don't need to take my word, because there was a whole workshop on last Saturday about these composable open source IPs. Therefore, it's desirable not to modify these external IP blocks like processor or accelerator cores, nor other cache hierarchy or memory controller changes. This includes not adding new instructions, nor to modify the ISA. However, we will still like to bypass the cache hierarchy for cache-averse accesses to reserve it for the cache-friendly accesses. Like in this specialized prefetching code, we are changing the indirect access A of B of I for a consume operation into Maple hardware. Our paper revisits state-of-the-art latency-tolerant techniques and identify their limitations, which are not only in performance, but also in ease of adoption. We figured out a way to mitigate indirect memory accesses without modifying the cores or the cache hierarchy. And in order to enable practical adoption of latency tolerance in many core SoC designs, we proposed Maple as a memory access parallel load engine, as a mechanism that implements decoupling of access and execute phases of an application, and a specialized programmable prefetching in this piece of hardware that is outside the core and connected to the network on chip. Maple's API operations for produce and consume can be targeted from off-the-shelf cores, like we'll explain more later. And thus the mechanism is agnostic to the core's ISA. So we could have cores of different ISAs. In a many-core architecture, Maple is the unit which is providing memory-level parallelism, so that even simple area-constrained in-order cores can mitigate latency. Unlike much of the prior art that assume beefy cores with large instruction windows and reorder structures. Maple implementation is a standalone IP block that has been taped out into silicon, so it's a reusable and also fully verified IP. A Manycore might have multiple instances, for example, one Maple unit per 8 or 16 cores, supporting the principles also of OS process isolation, where a process can map one or several Maple units to be shared across the multiple hardware threads. Our hardware RTL and software API supports virtual memory, and we evaluated it using Linux at full stack. We adapted an open source compiler pass to target Maple's API automatically for decoupling, instead of using the native executions of prior decoupling approaches. For the rest of the talk, I will be briefly explaining what decoupling is about and where we fit in the literature. Then I will explain Maple's hardware and software, how it works. Later, how we integrate Maple into the OpenPython Manycore and our results on that at full stack on FPA. Decoupling is a form of heterogeneous parallelism since the access and execute cores run in parallel. The key idea behind decoupling is that the access will run ahead of the execute and issue memory requests early and place it into a queue so that the execute will consume that data and perform complex arithmetic operations without waiting for memory at all, like we see in the upper timeline. However, the figure in the bottom shows that when applications involve long latency memory accesses, the run ahead is lost, and then the execute core is stalling, waiting for memory, and so the latency is not mitigated. So how do we solve this problem for many cores which are composed of in-order cores? Later, works like Desk solve this issue by asynchronously loading the data from the course pipeline to have memory parallelism. However, this involves deeper microarchitectural changes and new instructions. So it wouldn't be so easy to implement in the open source way that we wanted. And obviously, there's been a lot more work in this field in prefetching and load hosting. This is a subset of the work we studied. We have a more extensive literature in the paper, but we still found that we didn't see a software-only optimization that could work well with the skinny many cores of a Manycore, nor we found hardware techniques that couldn't modify the course of the memory hierarchy. So the main contribution intellectually of our paper is to leverage the compiler layer to target our specialized hardware, Maple, through its API, which only uses memory instructions targeted to the network on chip to reach the specialized hardware. And this is connected to the NOC in a nearly plug-and-play manner as any other block into the SoC. We're now going to explain our approach, starting from the compiler software layer and then explaining how we implemented the changes in microarchitecture level at Maple outside the core. So from the software side, although one could use the Maple API directly, we really programmers shouldn't do that manually. So instead, a compiler pass for decoupling slicing, like the one we reused from Desk, could divide the program into access and execute threads, and then call the API functions for produce and consume. Decoupling by itself doesn't give you latency tolerance. The memory operations need to be fetched in parallel, and the thin in-order cores of the Manycore only can fetch oftentimes one at a time. So our API implements decoupling operations targeting Maple to achieve better hardware memory level parallelism. Now we are going to learn how Maple helps, in this case, Core 1, to fetch many of the irregular accesses in parallel without stalling its own pipeline. The figure shows the sequence of the software and hardware steps of this produce of a pointer address into Maple, which they will then load it from main memory. The step 1, it starts doing a store operation into the Maple address space. Maple is a memory mapped I/O within the address space of the chip. So the fetch will reach Maple, also having as an offset the queue ID where we want to place the data for later to be consumed. Step 2, the decoder at Maple identifies the operation as the pointer produce, takes the virtual address of the pointer, uses the MMU to translate it to physical address, and then issue the store to memory in the step 3. Then step 4, the store operation containing the address that we mentioned is acknowledged back to the core, and then the core 1 considers the operation as finished. The request eventually reaches main memory, as it was issued previously by Maple, and then the response back to the issuer Maple, and then store it into the queues that are mapped as circulars FIFOs in the Scratchpad. From the consume side, step A, the execute thread will generate a load operation in the same memory mapped address space of Maple, which if the data is in the queue, step B will pop the head of the queue and then return the data back to the core 2 in this case, and the consumer operation is finished. And hopefully the data was already there, so the run ahead is achieved. So getting into the implementation details, I will zoom into Maple. And the figure shows the breakdown of Maple into these three main pipelines in yellow, and the queue controller and the MMU in blue, and we'll explain more about this logic later. The configuration pipeline is used to manage these queues and their binding to software threads. Queues are configured at runtime as they are implemented as circulars FIFOs using the Scratchpad. And at the end of the three pipelines, there is a stage where we reply back to the issuing core, whether it is a store operation or a load. Zooming into the blue box now that says Lima, this is our hardware unit to allow prefetch of whole loops of indirect memory accesses. This is what Lima stands for. Yeah, we fetch these things in hardware. So that was for decoupling before. Now we are going to explain how we support hardware prefetching. So some sparse linear algebra kernels have IMAs in tight inner loops. So rather than issuing every operation independently, we fetch the whole loop with just one prefetch operation into hardware. So given the two base pointers A and B and a range, Lima would fetch the whole loop in hardware and place the results on one of the queues that we saw previously from Maple, so that the execute core can consume it in a timely manner. We orchestrate with this single Lima operation, prefetching the loop so that it can later be consumed. So the previously indirect memory access now is changed to a consume in a streaming pattern from Maple. This has several advantages over software prefetching, such that we don't trust the L1 cache as the data is loaded non-cacheable from Maple. And it's also never evicted from the queue since it's living there. So, and there are other advantages that we mentioned in the paper. We have mentioned that our Maple API operations are under the hood loads and stores, so that the cores that interact with Maple, they map it to the corresponding physical page into virtual memory. So using virtual memory provides a process exclusive and protected access to Maple hardware resources. A process with many threads could also map several Maple units across the SoC, for example, in a tile architecture that we see in this figure. The API also handles the mapping process of the Maple units internally, providing an abstract concept to the programmer of software queues, which is also decoupled from the hardware implementation, so that the programmer or the compiler pass can use this without worrying about the internals. Now we'll explain how we integrated and evaluated Maple and its results. So as a part of a SoC design that we wanted to tape out, we integrated Maple RTL into the OpenPython Manycore on its own tile. For cores, we used the in-order OWASP-capable RISC-V Ariana cores, and the figure in the bottom represents a communication path of the Ariana core to Maple hardware and back. Our API operations translate into loads and stores instructions that read and write from and to Maple. For the evaluation, we are using an FPA chip prototype of 2 Ariana cores and 2 Ariana tiles and 1 Maple tile, and we have run the applications on top of Linux. Here we are comparing the same decoupled program using the Maple API implementation targeting the hardware and a shared memory implementation of that same API. We normalize it to the speed up of the traditional dual parallelism. The y-axis shows the speedup that we obtain with these fork workloads, and then the geo-mean speedup. So for SPNB and BFS, pure software decoupling is not effective due to the heavy load stalling on this area efficient in order core. And this is overcome by Maple, providing hardware memory level parallelism and achieving 2.3x speedup, and also outperforms dual parallelism across the board. Now, prefetching using Maple also provided 1.7x speedup over no prefetching, mainly also because of the reduction in the average load latency of 1.9x. Finally, we evaluated, this time in the Mosaic Sim simulator, up to 8 cores sharing the same Maple instance with 4 decoupling queues. So a single Maple can feed up to 8 consumed cores, so in total 16, by its 8 hardware queues. So this is one of the advantages of having this unit outside the core, is that the ratio is not 1-to-1 like you would have in a hardware prefetcher inside each core, but rather Maple can be shared by several cores at a time, so that we don't have a per core dedicated hardware. Now, to conclude, Maple enables both prefetching and decoupling, where its specialized hardware doesn't need architectural or core changes. And so, unlike many prior work, it's much easier to adapt just cloning the open source repo in such a way that it can be used in a SoC generator framework as a plug and play latency tolerance mechanism. Our full stack SoC FPA evaluation showed geo-mean speedups of 2.3x over software decoupling and software prefetching. And our hardware software co-design benefits from program knowledge and hardware specialization to achieve good performance at a low area overhead. Thanks for attending, and here you can find our open source repos for this project, demos, and our contact. Now I'm ready to take questions.
All right, do we have some questions? We'll start over here. Name and affiliation when you start.
Hi, great talk, Nick Lindsay, Yale University. So I've got a question. So you said you've integrated MMU into this Maple accelerator thing. So how do you make sure that the MMU, like the TLB, is up to date, and how do you do invalidations? Because obviously you're getting a translation and then filling buffers in using the translation. So you then invalidate the translation. What happens to all the data you've already filled in the buffer? Right.
So the MMU has full support, so it has its own TLB and page table walker, and even can support also page faults by we implemented with an interrupt. It could invoke our device driver, so it would support invoking the Linux to update the page table, and also supports shutdowns for making sure if there is a remapping of the page table to keep coherent.
Okay, thanks.
Other questions? Here we go.
Hi, Graham Gobieski, Carnegie Mellon. So I'm wondering if you quantified the additional NOC traffic that Maple introduces, and compared the Maple system to like a fully integrated, like a system that integrates the prefetcher into the core itself.
So the question is whether we evaluated against a more tightly coupled unit. Yes, you can find more details in the paper. We compare with the droplet hardware prefetching, which is tightly coupled to the core, and also with the desk, which is the, in a sense, the state of the art in like hardware decoupling, where these decoupling queues are more tightly connected to the core. So against, for example, the desk, let me show you one thing. This one. So there is some latency of going from Ariana to Maple and back. So this extra latency, in the case that we integrated with OpenPython in a different system, could be different too. And this could produce that for some, in the paper you can find that for some workloads, this could achieve a bit more performance because of just having lower latency to consume from Maple or in their decoupling the queues in itself. And so in that sense, there could be a performance difference. With Droplet, we were able to achieve more performance in every case, just because of the advantages of prefetches that we mentioned on the paper, of like the data is never evicted early, so you don't have to worry about having too much pressure on the cache because it's on the queue, so it will just be there all the time, and we are bypassing the L1 cache. So yeah, to answer the question, yes, we studied those things.
Thanks.
Thank you.
All right, let's thank the speaker one more time, and we'll start switching out.
All right, how does that sound?
Good.
All right.
So while he's bringing up his presentation, our next presenter is Nathan Blyer. He's a PhD student at the University of Illinois at Urbana-Champaign, where he is advised by Rakesh Kumar. Nathan's research interests are in architecture for emerging technologies and design automation.
All right, thanks, Dr. Dre. As he said, my name is Nathan Blyer. In this talk, I will present the first high-yield field-programmable flexible microprocessors, which we call FlexiCores. You're told multiple times every day that computing is everywhere. But truly, how pervasive are computers? RFID tags are not used to track individual fast-moving consumer goods. Computers have not enabled food packaging, which monitors freshness or checks to see if expiration dates have expired. Bandages and other low-cost disposable biomedical patches have yet to become smart. Our forests and parks are electronically barren. They are not full of sensors monitoring the health of wildlife or looking for invasive species. These domains remained untouched by computing due to conformality requirements, such as non-standard shapes or flexibility requirements, thinness requirements, and ultra low cost requirements, which cannot be met by even the smallest of commercial microprocessors. One possible solution is the use of flexible electronics. As the name suggests, flexible electronics are electronics which are bendable, conformable, or otherwise flexible. Researchers have been working on flexible electronics for decades. However, flexible electronics tend to have poor performance, power, and feature sizes which are decades behind traditional electronics. Flexible electronics use photolithography and printing technologies to deposit active and passive components on a variety of flexible substrates, such as polyamide, PET polyester, or even paper. Flexible electronics are poised to target a variety of applications in these computational deserts, because flexible electronics can meet conformality and thinness requirements. However, what's unclear is whether flexible electronics can meet the cost requirements of the applications in these computational deserts. Our goals for this work: show the feasibility of ultra low cost active flexible electronics, meaning they can be built at high volume and high yield. To do this, we focus on flexible microprocessors. We focus on microprocessors because they are general purpose, allowing NRE costs to be amortized over high volume relative to application-specific architectures. Further, some applications require some degree of programmability. To meet the ultra low-cost requirements of computational deserts, we want to build natively flexible microprocessors at high yield. As I mentioned earlier, although there is a plethora of flexible electronics technologies, we chose to do our work in flexible IGZO TFT technology. Here are some of the key characteristics of indium gallium zinc oxide thin film transistors, which are important to understand. Like many other flexible technologies, the feature size is extremely coarse, 0.8 micron versus today's 5 nanometer in silicon technology. Second, the max frequencies are in the tens of kilohertz range rather than gigahertz range. Third, most power is static power. And fourth, and most important for this work, it has high noise margin and high variability, and therefore building anything with more than a few hundred gates is going to be extremely challenging. How do we build IGZO TFT microprocessors that meet flexible application requirements? To answer this question, we need to better understand the domain applications. We looked at 20 different flexible applications from a variety of different domains, including environmental monitoring, health, and biometrics, and fast-moving consumer goods. The first thing to note is that the application sampled the environment at low rates, with no application sampling faster than 100 Hertz. Also, the data precision required by the applications is low, usually less than 8 bits, and oftentimes only a single bit. Compounding this, the frequency at which an application needs to run is also very low, with most applications needing to be run only once every several seconds, minutes, or hours. And finally, the type of computation needed for these applications is very simple. For example, all of these applications can be supported without the use of recursion. Combined, this means flexible applications have lax performance, expressivity, and data path width requirements. Flexible application requirements can drive architecture and microarchitecture decisions that enable high yield while minimizing energy consumption. We appropriately designed the ISA and microarchitecture of our flexible processors. We call these processors FlexiCores. FlexiCores are designed to minimize gate count, leading to high yield and low power consumption. While designing the ISA for FlexiCores, here are the key considerations. First, we would only support reduced data precision, since this is sufficient for most flexible applications and results in reduced ALU size, and for a fixed data memory budget, an increase in the number of data memory words. Next, we want a RISC architecture with simple ALU operations, enabling low gate count processor front-end and execution units. Due to the simplicity of the applications and their lack of recursion, we allied a call stack and indirect branching, opting to support simple branches to compile time targets. We want a Harvard architecture as opposed to a von Neumann architecture, which enables single cycle instruction execution, which in turn helps minimize energy consumption. And we want an accumulator architecture to enable single cycle execution with only a single data memory port. Similarly, here are the design constraints we use to design the flexible microprocessors, keeping the application and ISA considerations in mind. First, we are restricted to very, very small designs. I'd like to emphasize exactly how small 802 equivalent area is. The total area for our processor is 1/3 the size of a Cortex M0's register file, or slightly larger than the data memory of the PIC-10F200, the smallest PIC MCU architecture. We'll use no more than 8-bit wide data paths, as this is in keeping with the reduced precision data considerations and helps us achieve a small area. We want a single cycle execution, as multi-cycle and pipeline designs have area and energy implications. And we're limited in the number of IO ports due to manufacturing considerations present at the time of this research. We built 3 different FlexiCore designs: FlexiCore 4, a 4-bit version, FlexiCore 8, an 8-bit version, and FlexiCore 4 Plus, a richer version of FlexiCore 4. Here is the FlexiCore 4 ISA. FlexiCore 4's architectural registers consist of a 7-bit program counter and 8 4-bit data registers, which make up its data memory, and a 4-bit accumulator. 2 of the data memory locations are used for IO. Branching works as follows. A branch is enabled if and only if the most significant bit of the accumulator is set. ALU operations store the result of an add, XOR, or NAND operation into the accumulator. Load and store instructions enable moving data between the accumulator and data memory. The primary difference between FlexiCore 8 and 4 is that 8 has 8-bit words and thus an 8-bit accumulator. To satisfy the 802 equivalent area constraint, the data memory size is kept constant, meaning the number of words in data memory is reduced from 8 to 4. This ISA also adds a 2-byte sized load byte instruction, which stores an immediate octet into the accumulator. Once we've made these architectural and microarchitectural decisions, most of the design is straightforward. In the FlexiCore 4 design shown here, the decoder is stateless, with its output being a function of the current value on the instruction bus only. In the FlexiCore 8 design, the decoder has a single bit of state, enabling the 2-byte load byte instruction. The add instruction is supported due to the prevalence of integer addition in nearly all computing applications. We chose the other two ALU operations, NAND and XOR, since these instructions enable Boolean logic completeness while also being produced as byproducts of addition. Thus, the only cost of supporting these two operations is the inclusion of multiplexers on the output of the ALU. In order to determine whether this tiny design could achieve high yield and thus support low cost at high volume, we had to build and test some chips. Here are our fabrication results. First, we achieved a high yield, especially for the smaller FlexiCore 4 cores. Importantly, this is a commercially viable yield that can lead to sub-cent pricing. Therefore, IGZO TFTs can enable active electronics, which meet the stringent conformality, thinness, and cost requirements of computational deserts. Next, notice the high power consumption. These power numbers are similar to what we'd expect from a design with hundreds of thousands or millions of gates in a legacy process node using standard silicon electronics. The larger FlexiCore 8 actually draws lower power than the 4 due to a cell redesign which took place between fabrication of FlexiCore 4 and FlexiCore 8. In the 8-bit version, the resistivity of the pull-up networks was increased, leading to a decrease in static power consumption. But even with this process improvement, the power consumption is still very high. Thus, the energy consumed by flexible applications running on FlexiCores may be a concern. This graph shows the energy consumption and runtime for a set of simple kernels on FlexiCore 4 microprocessors, and therefore the higher the worse. Two things to notice. First, some take significant amount of time to execute. However, due to the lax performance requirements, the latency is not a major concern. However, energy consumption could be a concern as the devices are either self-powered or battery powered. Therefore, we need to look for opportunities to reduce energy while retaining high yield. Is there a better trade-off between area, yield, and energy consumption? One such opportunity could be considering code size in addition to gate count. Because we had made ISA decisions trading off ISA expressivity for reduced gate count, code density was significantly impacted. For example, performing an unconditional branch requires up to 4 dynamic instructions, while performing a logical right shift requires reversing the bit order, performing a left shift, and then reversing the bit order again, a rather clunky program. Therefore, one opportunity is to re-examine the operation supported by the ISA with a goal to reduce code size and instruction count. Based on analysis of kernel code, we identified several ISA extensions: add with carry, right shift, NZP flag branching, multiplication, accumulator memory exchange, and subroutine support, which would reduce code size. This graph shows the code size reductions enabled by each ISA extension on each benchmark kernel. While it's clear that all these extensions enable code size reduction, we still need to assess the overhead of supporting the extensions. This graph shows the normalized area, gate count, and code size improvement on a large benchmark program when using these ISA extensions. As we need to consider yield and thus area in addition to code size and performance, we selected these extensions, which provide a good trade-off between code size improvement and area overhead. On the other hand, we decided that the multiplier's usage was too limited to justify the large overhead. Similarly, we determined that doubling the data memory size, which has a large effect on area and gate count, is likely to affect yield negatively. Furthermore, although the built FlexiCores are single-cycle accumulator machines, it is worth exploring both the number of operands in each instruction as well as the microarchitecture of the FlexiCore designs. We looked at the number of operands for each instruction as well as the microarchitectures. Load store machines have larger core area but have smaller code size than accumulator machines. We also looked at multi-cycle and pipeline designs. Interestingly, the 2-stage accumulator design is actually smaller than the multi-cycle design, as the overhead of the controller and additional registers in the multi-cycle design were larger than the addition of pipeline registers in the 2-stage design. Unsurprisingly, this also reflects in energy trade-offs. To evaluate how these designs do in terms of energy, we ported the benchmark kernels to each of the new machines. These changes result in up to 56% energy reduction and 70% code size reduction with no more than 37% area overhead. To sum it up, we have highlighted that while computing seems ubiquitous, there are these vast domains which have not seen a proliferation of computing. And the reason for this is that these domains require conformality, thinness, and ultra low costs. What we show in this work is that while flexible electronics can meet conformality and thinness requirements, no natively flexible microprocessor has been shown to yield well. And in fact, no work has ever reported yield rates. That is until now. We show that it is feasible to build flexible microprocessors, FlexiCores, at a high yield, which enables low cost, provided that the right architectural and microarchitectural decisions are made. Thank you.
All right, do we have some time for questions? I see one over here.
Hi, my name is Karthik, University of Toronto. My question is, do you perform any sort of comparison if you were to implement exactly your FlexiCore on traditional CMOS, and what sort of gap exists between power, area, performance for that? And also, kind of a related question, is there anything in the work you presented or in the paper that is driven exclusively by the technology you're building, i.e. that this actually wouldn't work on CMOS and something would have to be fundamentally different?
So to answer the first question, we don't in the paper present what that would look like. However, we do know that it would, if you were to do that, if you were to take one of these FlexiCore designs and put it into a typical MCU process node, it would be about 25 to 30 nanometers per side. So you have very, very tiny chips that you would build in silicon. However, these are so small that they'd be severely IO limited. And due to scribing cracked stop ring sizes, if you actually tried to make them that small, you'd end up wasting the vast majority of your wafer. So the issue with doing something like this in silicon thus is you wouldn't actually be able to achieve those ultra low prices just by making a really small microprocessor in silicon. The second part of your question, do you mind repeating it?
It was, in anything in your implementation, was it fundamentally a mismatch with CMOS? And setting aside the manufacturing issue you mentioned, it actually couldn't be done.
Well, flexibility, of course. The big thing here is that we have these are built on a polyamide substrate. So the entire chip is flexible up to a 3 millimeter radius of curvature.
A question over at this side.
Sorry, John Demi, Microsoft. How do you deal with network? Because presumably these things need to talk to something. And how do you deal with non-volatile program storage?
Good question. I'll start with the non-volatile program storage first. We've actually just developed we've just prototyped some LP ROMs, so laser programmable ROMs. These are ROMs which you essentially build them as a typical ROM, but then after they've been manufactured, you go over with a laser and you remove some wiring, and now you have a programmable ROM. So these are a warm ROM that you can use to write your program into. The first part about network, that's an area for future research for us. There are quite a few ways to do antennas in flexible electronics. In fact, that's something there's a lot of research into. We didn't incorporate that into this work. Thank you. Thank you.
All right, other questions? Okay.
Have you looked into technologies like sub-threshold voltage to save power?
We have. The work from David Blau and the folks at Michigan is a big inspiration for us. The in terms of this technology, we haven't done that type of testing yet. So we're operating at 3 and 4 volts. I couldn't answer the question about what would happen if you tried to turn it down to, sub-threshold.
I'll wrap it up with one last question. You've presented a really good yield rate for such a tiny device. What's the cost point of this thing? Is it like pennies per device or sub pennies? How much do these things cost?
So working with Pragmatic, they have quite a lot of internal data. We were able to develop a cost model, which takes yield and area and volume and projects a unit cost. So with that, we're able to project a sub-cent price point at moderate volume.
All right. Let's thank the speaker one more time. Give me like test 1, 2, 3.
Can you hear me? Hello? Yeah.
All right, our final presenter in this session is Entropy Zhu. Entropy is now a second-year PhD student doing research at Apex Lab at Duke University. And Entropy mentioned that his research interest, and I found this interesting, is architectures for machine learning and machine learning for architectures. We got to get a battery change in the microphone, so.
Thanks. Thank you.
Thank you.
Thank you. This one should be right. Does it work? Okay. Hi everyone. My name is Entropy Xu. Welcome to my talk SNS. So SNS is a recursive acronym that stands for SNS is not a synthesizer. Like its name suggests, what we are building is not yet another hardware synthesizer, and instead we are building a hardware synthesized predictor that predicts for the hardware synthesized result, which includes the power, the area, and the timing of the hardware design. Logic synthesize is an important step in the hardware design process. This step takes the user's input hardware description language and produce a cell netlist as well as an estimate for the power, timing, and area of the input design. Having this estimate can help in several ways. They can direct the developer towards the area of the design that requires more optimization, and by performing synthesizing for a range of differently parameterized designs, this estimate can be used to choose the most optimum point in a design space exploration. However, synthesize is slow even for small designs. For example, synthesizing a small systolic array can take up to 1 entire day. This slows the feedback loop drastically, limiting the developer's ability to incorporate the synthesized result into their design process. And the slow synthesized process also makes the large space, high-dimensional design space explorations infeasible. Fortunately, recent advancement in deep learning gives us the tool to obtain approximate synthesized results way faster. In this presentation, I'm going to discuss how we are able to use modern deep learning techniques to predict the synthesized result 3 orders of magnitude faster than traditional synthesized tools. There are mainly 4 steps in our SLS prediction flow. We first turn the input hardware distribution language into a graph. Then we start sampling circuit passes from the circuit graph. With the circuit passes, we then predict for the physical characteristics of the pass. And finally, we aggregate the pass level characteristics to form the circuit, global circuit level characteristics, which is our final prediction target. To show what our work accomplishes, let's walk through a small demonstration, a multiply and accumulate unit, also called a MAC unit. We started with our design on the left. In this case, it's written in Verilog HDL. It can be converted into a graph intermediate representation using YOSYS, which is a open source synthesize suite. So each node in this graph represents a functional unit in the circuit, and each edge represents a wire connection between these functional modules. So you can see that the I/O ports in the Verilog code is converted into the vertices with the name of I/O, and the add and MUL vertices represents the adder and the multiplier units in the MAC unit, respectively. Now we have a graphical representation of the circuit. We can sample passes. We have wrong restriction for how we do this pass sampling, though. That all passes need to begin and end with either a I/O port or a D flip-flop. So in this example, we can have 3 passes being sampled. The first one, marked in red, originates at the top left 8-bit I/O port and ends at the 16-bit D flip-flop. We record it at the sequence of the vertices along this path. Following the same approach, we see another similar path colored in green. Since the circuit can have loops, paths can begin and end with the same nodes like the one marked in yellow. As you can verify that all these passes starts and ends with D flip-flop or I/O ports. The intuition behind this is that by having this constraint, we are effectively sampling the one-cycle passes from the register transfer level circuit. And this makes our following analysis much easier. Once we have enumerated the passes, the next step is to predict for the physical characteristics of these passes. That includes the area, power, and critical timing. But what model is best suited for this? We could use something simple like a linear regression model, but we quickly run into a problem. So let's consider an example below, where we have a multiplier and an adder arranged in 2 different orders. Naively, we would assume that synthesizing these 2 passes will result in the same identical area, power, and timing because they contain the same functional units. However, the synthesized tool can recognize that a multiply followed by an addition can be optimized into a simple MAC unit, which results in lower resource consumption than simply linking the adder and the multiplier together. But the issue is the linear regression model cannot distinguish these 2 passes as they have the same count of different types of function units. So the linear regressor will always produce the same result for these 2 passes. More importantly, there are tons of optimizations that a EDA software does to a circuit. And it is the job of the SLS model to learn how the EDA software optimizes these circuits. And that makes the linear regression model not suitable for this task. To remedy the problem we face with the linear regression model, we require a model that considers the adjacency, the ordering, and the frequency of the functional units in a path. This is a similar problem to the natural language processing, the NLP problem, where the meaning and the sentiment of a human sentence depends on the adjacency, ordering, and frequency of the words in the sentence. There's a model called the transformer model, which is frequently used in the field of natural language processing, and it is designed to precisely do this. Therefore, we developed a model called the circuit former, which is based on the transformer model, that instead of processing words in a sentence, the circuit former processes functional units in a circuit path, and it is able to infer the physical characteristics of that circuit path. We make the circuit former model much smaller and much faster than the original transformer model by pruning the original 100 million parameters into only 1.4 millions. So this model estimates the pass level characteristics at the far faster speed than traditional synthesized tools and with far greater accuracy than a simple linear regression model. Using the circuit formal model, we estimate the timing, area, and power of passes in our circuit. Now, we need to combine this result, this pass level result, to infer the characteristic of the entire circuit. As it turns out, a small multi-level perceptron model is sufficient to perform this inference. The reason that we don't need another powerful and complicated model for this is that all the details, all the structural and contextual details of the circuit has already been captured by the circuit formal model. This and the task of the MLP model is simply just to aggregate the pass level result into the global circuit level. Now, I have shown you how SNS works to infer the physical characteristic of full circuits without the long delay of traditional synthesizers. Our approach uses a variety of neural networks, which requires a lot of training data to produce high quality result. Unfortunately, the training data is scarce, and there's not a lot of open source designs that we can collect online to act as our training set. Therefore, to supply the model with sufficient training data, we have to generate and augment the training data ourselves. And this is how we do this. So first, we collect as many open source hardwares online as possible. This could come from a wide range of applications, for example, the Mac unit and some general purpose cores and some hardware accelerators. Next, we synthesize all these designs using a Synopsys design compiler, and this gives us a collection of the timing, power, area data for the full circuit of these designs. We call this data set the circuit level data set, and this data set is used to train the aggregation MLP model, which works at the circuit level. Well, for the circuit formal model, which infers the characteristics of individual passes, it is a more complicated, larger neural network, which requires more training data to produce high quality result. And this makes simply relying on collecting open source designs online not a scalable approach. To do this, we use a generative adversarial network based on SIGGAN that learns from existing passes and produce slightly mutated additional circuit passes. Both passes directly sampled from the open source designs and the passes being generated from the SIGGAN model are synthesized using the same approach like before. And this helps form a larger data set of pass level synthesized data. So now we have collected this larger data set, we can train the circuit formal model to a higher accuracy and higher robustness than was previously possible. Before we discuss the results we achieved by our model and our training set generation, it is important to understand how our model is different from prior work. One work that we learn a lot from is called DSAGE. So DSAGE is the GraphSAGE and graph convolutional based model that achieves great accuracy on predicting the timing delay of HLS designs. However, it does not fit well into the application scenario of SNS. The graph network-based approach does not scale well as it consumes infeasibly amount of memory to hold the large circuit with medium vertices that SNS is working on. But the GraphSAGE model behind the DSAGE provides us a hint that this large memory footprint issue can be solved using the idea of divide and conquer. And that makes us think of learning from the deep work model, which turns graph analytic problems into path analytic problems. And deep work turns out to fit very well to the scenario of the circuit analytics, as it allows us to encode the one cycle behavior of a circuit so naturally by just adding one constraint that each path needs to begin and ends with a flip-flop or a IO port. And more importantly, this approach scales very well, and we are able to achieve a very, very fast speed. For our experiments, we reserve half of the data set for training and the other half for evaluation. We show some of the accuracy results from our evaluation. We measured the root relative square error against the ground truth result and reported in this table. For this matrix, the lower the better. compared to our prior work, which performs only timing analysis, SNS lowers the error rate. The error matrix for power and area have no direct comparison, so we can look to see the quality of our result using the graph on the right, where we plotted the characteristics estimate by SNS as a function of the real characteristics. So with perfect accuracy, all points should lie on the diagonal line. And this plot shows that SNS achieves high accuracy for predicting the power, area, and timing of a circuit. But let's go back to why we make SNS in the first place, the need for speed. In this graph, we plot SNS execution time as a function of the execution time for the Synopsys design compiler. So the size of the each circle signifies the final area of the design. And we can see that for larger designs with larger die area, it achieves much faster speed compared to the baseline, compared to our baseline, which is the Synopsys design compiler. And what we found, and on average, SNS achieves 760 times faster speed compared to the Synopsys design compiler. Notably, this speed up was achieved using only CPUs to perform the neural network inference. And if high performance hardware such as the GPU is available, SNS can achieve an average speed up well over 2,000 times. We have shown you how SNS can produce high accurate result and so quickly for single designs. But how might this tool be useful? Let's consider an example where you are designing a say a general purpose processor like a boom core, which has many hardware parameters to tune. For example, we have the branch predictor, the fetch unit, the core width, the cache, the register files, the renaming buffer, and issue slots, things like that. You can name it. There are just so many hardware parameters. So we put important parameters for the boom core on the table at the right, and this is and by combining these like parameters together, we got over 2,000 possible configurations. And synthesizing all these 2,000 designs will take a really long time, around 45 days on a 96 core server. So instead of waiting a month and a half to figure out which configuration is the best, we can use SNS to quickly perform the entire design space exploration in a bit over 2 hours. SNS also achieves good prediction accuracy, which we can see in the bottom right table. The result of the DSE is plotted at the top left two graphs, and there we can see two very clear Pareto frontiers showing the diminishing single core performance with increasing area and increasing power. So in conclusion, in this talk, I presented SNS, which is not a synthesizer. It is a deep learning-based synthesized predictor that achieves high accuracy than prior work and drastically faster runtime than traditional synthesized tools. In practice, this enables highly accurate, high-dimensional design space explorations for large-scale parameterizable designs. And thank you for listening. I welcome any questions.
All right, we have time for a couple of questions. Oh, we'll start here and then I'll jump back there.
Oh, hello. This is Fang Jia from Purdue University. It's an amazing work. One thing I am a bit confused about is, so in one of your examples, when you said how you extract the paths from the net list, in some cases, one cell might be counted in multiple paths. For example, in the moadd case, the add, the multiplier, they are counted multiple times. And for each of these paths, you assign a power to them. So when you are summing up these paths together, aren't you recounting the power for each cell many times?
Yes, that's a very good question. And that's one main challenge in our design process when we're doing this model. So our solution to this problem is that we designed a sampling algorithm that is not just purely random. And I mean, it's based on some randomness, but the idea behind it is that it guarantees a uniform distribution over the entire circuit, even though there can be some repeated passes like like one vertices in the graph can be traversed more than one time, but overall, statistically, it is still uniform.
All right, and next question.
Hi, this is Charles Hung from UC Berkeley. So I guess I know that given the format of your input data, like the paths, it might be hard to do like an apples to apples comparison with a lot of other like ML methods, but were there any other like simpler methods? I know you mentioned that it seemed like linear regression probably wouldn't work, but I guess, was there any evaluation of those sorts of methods that you did? And could you comment on like how much worse they were? I guess.
Yeah. So I see. So, well, we for the input of our model, we take Verilog source code directly. We don't take graphs as our input. So if you are looking for some comparisons with a machine learning work, so in the machine learning models, like the graph stage, they don't consider like the D flip-flop as a special node, which affects like the mini sampling that like, which is a term they used to like call their like divide and conquer method. Yeah.
All right, let's thank the speaker one last time. And thank everyone who presented in the session today. I think we're moving into the break just a little late, so it'll be a little short.